Alright, so we're going to go ahead and start Chapter 6 this semester. Um, the last part of Chapter 5 is pretty complicated, and um, we might go back. I don't know. It's probably not worth all the tedious math to go through and compute all those choose functions and everything, um, those probabilities. But it is important. Um, anyways, we're here in Chapter 6, and we're going to talk about probability distributions, but a particular type of probability distribution that's the discrete type, or I should say a class or a set, because one of the concepts that divides math into basically two different fields. If one of the first divisions that you can have in math is between the continuous and the discrete. And really, it can get very philosophical, like whether or not it makes more sense to think of the universe as a continuous um, thing or as a set of discrete things. It seems like you're more accurate if you think of it as discrete. But point is that a discrete random variable, which we've talked about, is a random variable um, that has a countable sort of an outcome that you can list out all the possibilities basically, like the number of eggs in a carton. It's going to be between 1 and 12, or the number of dollar bills in your wallet. However, something that's usually measured, like a length, the height of the football team, maybe, or the amount of water in a jug. That these are continuous things. So you can have somebody who's 5'11", somebody who's 6, or a bunch of possibilities in between, right? So that's the difference between discrete and continuous. Discrete is like the number of eggs in a carton. It's something that you count at 1, 2, 3, 4, 5. So we're dealing with this type, because continuous you need a little bit more advanced math to talk about, um, um, to really understand more completely. So the point of math to start is to predict, right? That's why we do it. Really, if you look at the history of math, in my opinion, it's just a bunch of documentation of how somebody was able to write down their thoughts on how to solve a problem without actually having to do the whole thing by you can maybe build one pyramid for the Egyptians, and instead of having to experiment every time, why don't we write down the instructions and the geometry and the angles and the ratios of the different sides and everything. That way we don't have to you know make the same mistakes over and over again. So math is just a very, very rigorous way of doing that, and you end up talking about these things called functions, which are really just these very nice. A lot of times they look like equations that you plug something in and you get one answer back out. So it has that predictability about that in there. So what I'm going to explain right now is that we're kind of getting away from the idea of functions a little bit, because we realize that the real world doesn't always behave so predictably. Um, we can kind of see what's going on, but sometimes we can just assign probabilities to things or likelihoods to things, and we can't say this is going to happen every time. So I'll give you two scenarios. Scenario one, we're going to drop a ball from a building, right? And I've given this before, I'm sure. I drop a ball off from a building, or I throw it maybe, and it takes this kind of a path, right? So I can, draw a graph here with time and with height maybe, and the height of the ball uh, would look like this as time goes by. Kind of that same shape. Even though these aren't necessarily, uh, they look like they're the same thing, but they're talking about two different things. This is actually the position, and this is the height versus time. So if I were to do this the same way, let's say this is 100 feet in the air. If I were to throw the ball the same way with the same amount of effort, wearing the same clothes, with the same uh, scenario and weather every single time for 1,000 times, right? I'll get the same path. I'll get the same path 1,000 times, right? This is the deterministic way of thinking. And this is also a big classification in math, the deterministic versus non-deterministic. Um, so I do this 1,000 times, I'll get the same path 1,000 times. Um, and so I can build a function here. I can build. I say this is very predictable. So I have the height, which I'll call y, is equal to the initial height, 100 feet, um, plus the initial velocity. Actually, really, it's just going to be minus 16t squared, right? That's actually what it would be if you were to look it up in like a college algebra book or something. Or so I can plug in a time, and since we know the height of the building, it'll be that. So I just plug in a time, 2 seconds. I know exactly where this thing's going to be. Okay, and that's a scenario. This is again the deterministic. It's not a very manly color, but whatever. Okay, scenario two. Now I'm going to drop a ball, but I'm going to add a little bit more reality into here. Right? I'm gonna drop a ball, um, but let's add some wind. Right? Let's say it's a very windy day, and the wind is doing that thing when it's just kind of there's gusts and it blows almost vertically, kind of hits the ground and it goes up. So now we try to drop the ball from the building, and we'll do it once, and maybe it'll kind of take this path where it'll go down, and then maybe it'll kind of get pushed back up, and then it'll kind of fall down again. We do it another time, and maybe it'll take this path where it'll just the wind is not really blowing, and it takes kind of the path that we were used to. And maybe we're doing this 1,000 times, right? So we do it yet another time, and maybe the wind's blowing really hard, and it just kind of sustains the ball up there for a while, right? And it takes this path. So with this scenario, because of the wind, and the wind is not blowing in a very nice way, you can't really predict, right? So do this, whoops, 1,000 times and get 1,000 different paths. Okay. So this is what we would call random, right? If I were to actually list out all the different paths, maybe I try to draw a graph, and I would maybe get the first one that I tried. It's this one. And then the second one that I tried, and I got this. The third one I tried, and I got this kind of a thing. Maybe I try a fourth one, and I'll get something that maybe looks even weirder. Maybe like this. I don't know. Something like that. And have you ever seen on the Hurricane Center or the Weather Channel or something like that? Well, they'll show you the outline, the different paths, models that a computer might generate for a hurricane to go in all those different directions. Well, that's kind of this is a very simplified example of that, where you can't really predict what's going to happen. And actually here we actually did the experiment and we recorded our results. There they're trying to predict, but it's the idea that there's just a bunch of different possibilities. But some of them are more likely than others. So there is some sense of coherence. You know, it's not all just complete chaos, I guess. So in scenario one, we would call T a deterministic variable, right? It always has the same outcome. I would call it deterministic. I think that's the right word. So it always has the same outcome. I do it 1,000 times, I get the same path. I can write a nice little function for it, and the world's a nice place. But then reality sets in scenario 2. I just throw a little bit of wind in there, and I would call t, the same variable, I would call it a random variable. And instead of talking directly about the height at a given time, because that's what I was doing here, I was talking directly about the height. There's a very clever thought process that was developed in the 1900s, and really games of chance and things like that, poker and rolling dice and things like that have been studied for thousands of years. But as it became more and more relevant to study in the sciences with quantum mechanics and things like that, Russian mathematician Kolmogorov decided to kind of mathematize this probability, this idea of probability spaces, and he came up with something called measure theory and a bunch of stuff that only if you go really far in math you'd ever know. I don't even really know it that well, but it's neat to talk about. Point is that instead of talking directly about the height at a given time, you talk about probabilities of the height, or the likelihood of the height at a given time. Because I don't know exactly what the height's going to be, but I can know where it could be, and I can assign a number to that, that I'll call a probability. So, definition: a probability distribution, right, assigns a number to the output of a random variable such that the number falls between 0 and 1. I'm trying to be very exact with what I'm saying, but really it's what we've seen, that if I roll a die, then the probability of getting any number between 1 and 6 is always going to be between 0 and 1. Really, it's 1/6, which is a decimal. That's what this means. And if I add up all the different probabilities of all the different scenarios, events in my scenario, then I'll get 1, right? So, and this right here, this expression would be different if it were continuous. I would draw an integral symbol. So this is, again, we're talking about discrete probability distributions. We will talk about continuous distributions, but not really in a way that we'll fully understand it, to be honest with you. You're going to have to use tables in the back of the book to find your probabilities, because you haven't learned to integrate. And that's something you have to learn in calculus. But this is the fact that we're taking a sum, a finite sum, is because we're dealing with discrete probability distributions. Okay, so that's what's happening, is that we're not just talking about time, or where the ball's going to be at a given time. We're going to talk about where could it be and how likely is it to be there. And that's what a probability distribution is going to tell us. And I'll give you an example. I said rolling a die. So what are my likely outcomes when rolling a die? So I have my die, right? And my sample space is what? It's 1, 2, 3, 4, 5, 6. These are all my possible outcomes. So really, my random variable is this is gonna be the range of my random variable. So my random variable is gonna be 1 through 6 in this scenario. It doesn't have to be 1 through 6. A random variable, there's an exact way of defining it, but until you understand that, it's kind of subtle. I could say my random variable could be money if this is a betting situation, where if I land a 1, then I get $1. If I land a 2, I get $10. If I land a 3, I get $100 or whatever. If I land a 4, I pay $50. So I now my random variable is money. You see, it's money that's assigned by each of these numbers from rolling the die. So it doesn't always have to be just from the die or flipping the coin heads or tails or something like that. But okay, so in this case, my random variable is going to oh boy, I don't want to write this in a way that's too confusing, but this is the best way I can think to write it. So the output is going to be 1 through 6 again. Okay, just remember that those are all my possible outcomes. 1, 2, 3, 4, 5, 6. What a probability distribution is going to do is it's going to take each of those numbers, 1 through 6, and it's going to say, okay, give me something between 0 and 1, right? So the probability, and really what we would do is we write it, we're going to do in this chapter is we're going to write it in a nice table like this. So here's my random variable. In this scenario, it's just 1, 2, 3, 4, 5, and 6. And my probabilities are going to be 1, 6, 1, 6, 1, 6, 1, 6, 1, 6. This is like a frequency distribution that we did in chapter 2. This is how you're going to write it. It's a kind of a clear way at this level of how to write it. Yeah. So now again, I could be rolling a die again, but I could give you a different scenario. I could be talking about money. So let's say we were betting, even though you shouldn't bet. But let's say we were. If I get a 1, let's say I get $2. If I get a 2, let's say I have to pay the guy $1. If I get a 3, I gain $4. And then 0, everything else, okay? So now my random variable, you see my random variable is taking these numbers, the sides of the die, and assigning something else to them. Not necessarily, it's assigning money to them. And now I still attach a probability to that dollar amount, and that probability is still going to be 1, 6, 1, 6, because it's associated with rolling the different sides of a die. Okay. Now what we do is we want to have some things about probability distributions that show up every time that we can consistently talk about, and those things are the expected value, which, if we remember from chapter 2, what we did is we took all the frequencies and multiplied by the midpoints, and we added them up, and we got the average, right? So we would call that mu. That was our way of getting the average. Well, we're doing that again here. And then we have something called the variance. So the variance is the sum. That's our the square of our standard deviation. And now we're going to think of it like this. Right? It's a bit of a different way of getting it, because before we just had raw data, and we were taking that raw data and we would compute the variance. Now we're talking about a probability distribution which says we know a lot about our data now. We know that the data, the likelihood of the data looks a certain way if I were to draw it all out. And so now we can compute it this way. Okay? So these are the two things we're going to talk about: the expected value, the average, and the variance. And just get used to these formulas. That just means, remember, this means add everything up. When I see that symbol, sigma, it means add everything up. Okay, so rolling a die. Now, the thing is, I don't have an equation. I don't have like not necessarily a function, but I don't have a formula to describe this. It's just a table, a set of ordered pairs that I have. With a binomial distribution, you know several things. You know that there's independence. Remember, where like flipping a coin, getting heads on one try doesn't affect whether or not you get heads on the second try. So you have that, and then you have one of two possibilities, and you have a few different things like that. If you have all that, then you have a binomial distribution, and you can write a formula to get what you want. And it looks like this: the choose function times little p. This is not the same p here, x, and this is q of x, where p is called your probability of success, or getting what you want. And then q is your probability of failure. Probability. Okay? So what you're doing is you're counting up all your different scenarios that you could get, and then you're multiplying by, oops, this is n minus x here. You're counting up all your scenarios, and then you're multiplying by, sorry, somebody came in the room. So I was talking about the binomial distribution, and oh, okay. What we're doing here is we are taking this, uh, we're counting up all the different possibilities with the choose function, and then we're multiplying by the probability raised to a power. So um, best way to understand it is, let's say I wanted to know the probability of getting 8 tails, right? If I flipped a coin 10 times. So I have to give you the very specific scenario, but this is a binomial distribution. There's two possibilities with flipping a coin, and my p, the probability of getting tails, would be 0.5, and my q is equal to 0.5. This is not always the case. I mean, sometimes in, like, maybe if we did a genetics problem, the probability of having blue eyes might be 1/4, and the probability of having brown eyes might be 3/4. So my p would be 1/4 and my q would be 3/4. So it's not always half and half. Okay, but n is the total number of times that you did the experiment. So we would say 10 choose, 8 is the number of times you want to get tails. P is the probability of getting tails, and you raise that to 8 times. I want to get 8 times, so these are independent events, remember, and it just gets raised to a power because the last one doesn't affect the previous one. And then I want to make sure that the other 2 times I got heads. So the probability of getting heads is 0.5, and this is going to be 2. So all of this will give me my probability of getting exactly 8 tails. Okay? And that's how a binomial distribution works. And this is kind of a nicer way of talking about distributions at first, because that way you can kind of see, oh, I have like a kind of an equation here, and this is what it's going to give you my distribution. It doesn't always look that nice. It doesn't always look like an equation. The previous example I did, it's just a table of the different possibilities. But yeah, so that's the idea behind distributions and probability, and that's what we're getting into. And oh, and another thing, this is a general formula. So if you're given just a list of data, if your probability distribution is just a list of data, and you need to compute the average or the expected value and the variance, then this is what you use. But if they say, oh, it's a binomial distribution, then you have a more specific formula. For a binomial distribution, your average or your expected value is just n times p, or the total number of times you did the experiment times the probability of success. So my expected value for this example is 10, the total number of times I did the experiment, times the expected value, or times p, so it's 5. So my average number of tails is going to be 5, right? Which makes sense. It's going to be half. My variance is going to come from m times p times q, which is it's just a measure, again, of how spread out the data is, how wild or how varied the data is, right? So okay, let's see. That's a good intro to this section. Let's go ahead and compute some things. Let's do some examples. Oh, well, I just did example 6.1. So example 6.1 on page 212, it says write the probability distribution for rolling a die. Whoops. Construct, whatever, a probability distribution for rolling a die. And they basically wrote this. They wrote it sideways. So example 1, page 212. And they did this. They said x, p of x. And they wrote 0, 1, 2, 3, 4, 5, 6. Whoops, there's no 0. 1 6 1 6 1 6 1 6 1 6 1 6. Okay, same thing I did. Okay, example 6.2 says represent graphically the probability distribution for the sample space for tossing 3 coins, or basically tossing a coin 3 times. Same thing. So we can write out the distribution again. They like to write theirs sideways, whatever. So x would be the number of heads. That's what they're doing. Okay, so what's the probability of getting 0 heads? The answer is 1/8. If you were to actually do it, remember how we listed out all the possibilities? Heads, 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 tails, and so on. There was 8 total possibilities, which is the bottom, and there's only one way to get 0 heads, and that's if you get all tails. And if you were to list out the whole sample space, it'd be 1 out of 8 total possibilities. So 1 out of 8. How many ways can you get 1 heads? You can get the first one to be heads, the second one, or the third. So that's 3 out of 8. And then thinking similarly, 2 heads is 3 out of 8. And then 3 heads would be 1 out of 8. So if you graph it, it looks like my probability, my x, and then just mark off, all right, 0, 1, 2, 3. So getting 0 heads is 1 out of 8. Getting 1 heads is 3 out of 8. 2 heads is 3 out of 8. And 3 heads is 1 out of 8. Okay? So that's the graph of what it looks like. If I wanted to compute the expected value, they're not asking for this, but let me just show you how to do it. It's going to be the sum of all the probabilities times the range of my random variables. So I would do 0 times 1 out of 8 plus 1 times 3 out of 8 plus 2 times 3 out of 8 plus 3 times 1 out of 8. So this ends up being, this is 0. So it's 3 out of 8 plus 6 out of 8 plus 3 out of 8. So this is 3 plus 6 plus 3 out of 8, which is 12 out of 8, which is 6 over 4, 3 over 2, so 1.5. So that's my expected, which really falls right in the middle. That makes sense, because if I were to, the expected number of heads that I would get is right here, right in the middle, 1.5. I would expect that half the time I would get heads. So even though you can't get heads 1.5 times, it's still showing how I guess it just makes a lot of sense that if you're flipping a coin, half the time you should get heads. So okay, there's that. During the summer months, a rental agency, no. Let's see. Oh, this is good. Example 6.4. This is page 3. So determine whether each distribution is a probability distribution. So rather than writing it, I'll just show you. We have this. Okay. So determine whether each distribution is a probability distribution. Well, remember, a probability distribution is no longer, it's not like a function. It's not very nicely behaved, but we have 2 rules. We just got to fulfill 2 rules, and that's that they have to add up to 1, and that all the probabilities have to be less than 1. So let's zoom in a little bit here. Okay, so let's just look at this. If I do well, clearly the first one's satisfied, and it actually gives the list of requirements right here. So, uh, I'm sorry, the second one's satisfied. All of these are numbers that are less than 1, 1/5. Okay? And then if I add them all up, 1/5 plus 1/5 plus 1/5 plus 1/5 plus 1/5, that equals 1. So A is a probability distribution. Let's try B. Automatically fail because -1 is not between 0 and 1. So we're not fulfilling this requirement. This is not a probability distribution. What does it mean to have a negative probability, right? It makes no sense. Letter C. Okay, it looks like it might be because all of these are less than 1, so I fulfill this requirement. And then if I add everything up, I actually end up getting exactly 1. So it is a probability distribution. I actually have to do the work with my calculator, but 1/4, 1/8, 1/16, and 9/16 all add up to 1. D looks like it might be, but let's add them up because these are all less than 1. So again, this is good, but do I have this requirement? So 0.5 plus 0.3 is 0.8 plus 0.4 is 1.2. So we're bigger than 1. This cannot be a probability distribution. Okay? All right, so that takes us to the homework, the first homework, so we'll go ahead and stop there.